Now let us move on to properties of the Z transform. Now most of the properties resemble their counterparts for the Laplace transform. So we can be very brief and quick with this discussion. First property, linearity. So we have that A x1n plus B x2n transform to A x1 z plus B x2 z. Now the ROC R of the whole combination is normally equal to R1 intersection R2 except when pole 0 cancellation occurs at the boundary of R1 intersection R2, and when that happens, or if that happens, then the ROC extends towards either the next pole or infinity or 0. So more appropriately this should be this R, the overall R of the combination, the region of convergence of the combination is a superset in the most general case of the individual ROCs R1 of x1n and R2 of x2n. So much for our discussion of linearity. Next, time shift. In a most straightforward manner, you get that x n minus n naught transforms to z to the power minus n naught x z. Okay. Now what about the ROC? R dash is the ROC of x n minus n naught. How does it relate to the ROC of x n? It is practically the same except for the usual caveat. Except for z equal to 0, which has to be excluded if n naught, I mean if x n minus n naught has points on the right side, that is if x n minus n naught is not equal to 0 at any n greater than 0, or except for z equal to infinity if x n minus n naught is non-zero at some n less than 0. Frequency shift. this is interesting and it affects the poles and zeros in a very complicated manner. So, let us look at it. What we are saying is, suppose we have x z minus z naught. What happens to x z minus z naught? What is the inverse transform of x z minus z naught? Now, if x z minus z naught is given to us, then we can apply the inverse z transform formula, which says 1 by 2 pi j r e to the j minus pi to r e to the j pi of x z minus z naught e to the z to the n minus 1 dz to get what will turn out to be z naught to the power n x n. So, this is the sequence that we will get. Now, let us understand z naught to the power n x n by taking its z transform once again. We ought to really get the same thing, but we will get it in a different appearance. Z naught to the power n x n will transform to summation over n x n z naught to the power n z inverse, which is equal to summation to the power summation over all n x n z naught by z, or rather z by z naught to the power minus n. Fine. So, essentially it is the z transform of x n against the variable z by z naught in lieu of z. That means wherever z had a pole or a 0, now z by z naught will have that pole or 0. That means to say that all poles and zeros which are at points zk and pk will now shift to points z naught pk and z naught zk. If x of z had poles at pk, zeros at zk, then x z by z naught has poles at z naught pk, zeros at z naught zk. Thus, the ROC expands by an amount mod z naught. For example, if z naught were equal to 2, all the pole magnitudes would multiply by 2, all the 0 magnitudes would multiply by 2, as well as the ROC expands by an amount mod z naught equal to 2 and rotates by an amount angle of z naught equal to omega naught. Rotation of the ROC, however, has no impact because they are all circularly symmetric. So, anything which circularly symmetric about the origin can rotate freely without bothering us, but the poles and the zeros will also rotate, and that is important to understand. Rotation of the ROC makes no difference, but we must remember that the poles and zeros also rotate in their positions by omega naught. Apart from expanding, by mod z naught. So, let us take an example. Suppose we say z naught equals 2 e to the j pi by 2. Let us say this is z naught, 2 e to the j pi by 2. Now, let us take a pole 0 plot. That is the unit circle, and let us put a few poles over here. Let us have a pole at 0.5 and let us have a pair of zeros at say here and here. So, there are two zeros in green and there is a pole in yellow. The pole in yellow is at 0.5, 0.5. The zeros are at 45 degrees and minus 45 degrees. Remember that poles and zeros must all come in conjugate pairs if they are not real. If they do not, then the coefficients of the difference equation from which the Hz has been elicited will not be real. It is the same argument as before, there is nothing new. Okay, now we have this and we have z naught given by this. Now, mod z naught equals 2. So, everything gets farther away from the present position, everything blows up by a factor of 2. So, if this was the unit circle as we have assumed it is, fine, then we will see what happens to the new. The unit circle is still there, of course, the unit circle is not part of the function. Then you have the 0.5, the pole at 0.5 shifting by, expanding by 2. So, 0.5 becomes 1. Also there is a rotation by pi by 2. So, the pole now lands up here. Magnitude has doubled, rotation of 90 degrees. Now, these two zeros which were there on the unit circle at minus 45 and plus 45 degrees, omega equal to minus 45, omega equal to plus 45, the one at omega equal to minus 45 and of magnitude 1 will become magnitude 2 and shift to plus 45. So, you will have now the new poles placed over here and over here. The entire thing rotated by 90 degrees. The relative positions remain the same. The relative angular positions of the poles and zeros are maintained, but they have expanded and the whole system has rotated. So, this is how it relates to frequency shifting. Next property. time reversal. If x n transforms to x z, then x minus n will transform to summation over all n of x minus n z to the minus n, which will turn out to be equal to x of 1 by z. So, what is the ROC? If this was with an ROC of R, what will be the ROC of this? Let us first try to understand where the poles and zeros will go. Now, if you had a 0 or a pole, some singularity at say zk, now 1 by z, earlier it was at z equal to zk, now it is at 1 by z equal to zk, that is at z equal to 1 by zk. So, what happens in the pole 0 plot of x of minus n is that everything gets flipped over the unit circle. All poles zeros flip over the unit circle. Now, apart from their flipping over the unit circle, the entire ROC also flips over the unit circle. That is to say, if z naught was in R, now 1 by z naught is in R. So, let us make up an example again. Unit circle, and let us say there are poles at this place and this place, that is plus or minus 45 degrees with a magnitude of 4, with a magnitude of with an angle of with magnitude of 0.5. Okay. So, now what will happen if we take x, this is for x, sorry, this is for x z. So, what will it be for x minus n? It will be x 1 by z. So, let us plot that, x 1 by z, unit circle again. Now, these two get thrown over to the other side of the ROC. Suppose this had an outward ROC. Let us say that where R is given by this. Let us go back to the first one and complete the story. So, it is an outward ROC starting at 0.5, because you have a complex pair of poles at 0.5 magnitude and 45 and minus 45 degrees. Now, these two will go to these new places, same direction of course as before, but now the poles are at the reciprocal of the present magnitude distance. So, they are somewhere over here, sorry. And here, this is where the poles now are located. And also the ROC gets inverted. It was outside of 0.5 earlier, now it will be inside of 2. So, you will have to make an annular boundary over here like this, and fill it up inside. This is what you get, an inward ROC, but it extends all over inside the unit circle and everywhere. This is the ROC of the new function. Now, it is evident that if xn was right sided, then x of minus n is left sided. And that is borne out by this inward ROC left sided, outward ROC right sided, and that is what is happening. Fine. This is for time reversal. Next, let us go to the next item. Convolution. This is pretty straightforward. All we have to say is that x1 n convolved with x2 n will map to x1 z times x2 z. The proof is practically the same as usual. Furthermore, R dash is a superset of R1 intersection R2, just like in the case of linearity, with expansion beyond R1 intersection R2 occurring when pole 0 cancellations occur at the ROC boundary of xn of x1n into n x2n. If there is no pole 0 cancellations, then it will be the intersection. Even if there are pole 0 cancellations, but they are inside and not at the boundaries, it will be the same. Expansion occurs only if any outer pole or inner pole, any boundary pole gets dislodged by cancellation with a 0. Next, Z domain differentiation. Differentiation in the Z domain. Now, what we are saying is, if we differentiate xz with respect to z, what happens? This is easily found by using the normal z transform expression and carrying out the differentiation. You have x z equal to summation over n of xn z to the minus n, and so if you differentiate it with respect to z, d x z with respect to z equals summation over n. The only thing that weights differentiation here is z to the minus n, so it becomes x n z to the minus n minus 1 multiplied by minus n. That is what you get. So, carrying out appropriate manipulations, you get that z times dx z by dz is the transform of n minus n x n. This is the expression you get for the transform. Now, if xn has a certain ROC, n times xn will have the same ROC, because multiplying by a linearly increasing sequence will not affect the ROC, since the modifying function used in the Z transform is exponential. So, it makes no difference to modification by a linear function, the ROC does not change. So, this brings us to the end of the properties. Finally, along the lines of our discussion regarding the properties of systems described by Laplace transforms, whether they were causal, whether they were stable, etc., we can make similar remarks about systems, LTI systems, about their stability and causality on the basis of the poles and zero locations of the Z transform, of their Z transform. In order to do this, we will just note the following arguments. First, a system with impulse response Hn is stable if Hn is absolutely summable. That is, if it has a DTFT, that is to say, if the ROC of Hz contains the unit circle. That is what we know. Second, if the system is causal, then Hn is right sided and ROC of Hz is outward. Taking 1 and 2 together, from 1 and 2 we find that if a causal system is to be stable, all poles must lie within the unit circle. Since an anti-causal system will have a left-sided Hn and an inward ROC, it similarly follows that for it all poles lie outside the unit circle. So, that neatly winds up the kind of conclusions one can come to about stability, causality, etc., of discrete time systems on the basis of the poles and zeros of the Z transform of the system's impulse response.